Hello everybody, I am Vasil Vasiliev and this is my colleague Garima Singh. Today we will be talking about floating point error estimation using automatic differentiation. Floating point errors can be important for high precision calculations or regular repetitive tasks. The code example here shows a simple case of repeated addition and subtraction to a single value c for 100 million times. For every even iteration, we subtract the value from c, and in each odd iteration, we add a value to c. Depending on the rounding mode, the answers can be very different. For the IEEE double precision standard, none of the rounding modes even comes close to the answer provided. Here you can see that the mathematical formula that the algorithm describes yields an exact solution of -50. This simple and maybe pathological example underlines the limitations of the floating point representation. Often to mitigate floating point errors, we use extended precision or even other types of compensation algorithms. But in this talk, we will see, can we detect such anomalies in algorithms in an automatic way? The floating point representation limitations are everywhere. Floating point stability is of key importance to many data-intensive sciences, which work with increasing data volumes, but also in heterogeneous environments. For example, using a single or double precision can make a significant difference in performance, as many GPUs may not even provide a compliant IEEE floating point representation. Our main field of interest is the field of energy physics, which works with hundreds of petabytes of data per year. The data taking process sifts through the large volumes, trying to find interesting data in order to optimize the required storage and reduce the reprocessing costs. A robust and automatized detection of floating point errors can help reduce the computational costs of physics data processing, and in addition, it can help developing novel lossy compression solutions. There are multiple ways to estimate floating point errors. A very common one is to explore the representation limitation using Taylor series. Here, h can be thought as the maximum floating point representation error in the input variable x. Then we can write an expression of the absolute maximum error in f as, using the first order approximation of Taylor series leads to this, where h is represented as the product of x and the machine epsilon. The machine epsilon gives the maximum relative representation error in the floating point variables due to rounding, and it is machine dependent value. From here, we can say that the approximation of f, of a of f, considers the first order derivative at xi, takes into account xi and the machine epsilon. A more general representation of the floating point errors in arbitrary dimensions is the following, where a of f is the absolute error in function f, xi is all inputs and intermediate variables of that function, el is the error due to the linearization of the Taylor series expansion, en is the upper bound on the relative approximation error due to rounding, that's the machine epsilon and it's machine dependent, df dxi is the derivative of f with respect to xi, and here in that formula we will see that we can get the values of df dxi using algorithmic or automatic differentiation. We know em, which is the machine epsilon. El is hard to estimate and outside of the scope of this presentation. Here we will see that even if we don't have a good understanding or don't have a good estimate of el, we can reason about pretty well floating point error estimations. The formula gives a good upper bound on the error and serves a general use case. However, more complex analysis may solicit closer error bands. For example, using the second order Taylor series and so on. As we will see later, this can be achieved by using custom models in our framework. Here, automatic differentiation provides a good tool for calculating the partial derivatives in function with respect to its inputs and intermediaries. Automatic differentiation can give us an exact and scalable way to produce df dxi from the formula from the last slide. AD applies the chain rule of differentiable calculus throughout the semantics of the original program. For a complex nested function like f of g of h of x, AD defines major recursive relations which affect the way we decompose the computational graph. The forward accumulation mode starts decomposing from function inputs to function outputs. This means we need to run multiple times to get the derivative at each direction. Reverse accumulation mode starts decomposing from function outputs via all intermediaries to the function inputs. This matches quite well the requirements from our previous slide, and also importantly, it gives us an algorithmic time complexity that's independent on the number of inputs. In the context of floating point error estimation, we'll use the reverse mode AD. There are multiple approaches to implementing automatic differentiation. At the two extremes are operator overloading and source transformation. The operator overloading approach is easier to implement, but defers many operations until runtime, where fewer code optimizations can be applied. Whereas source transformation is harder to implement, but tries to do as much as possible at compile time, including regressive optimization. The framework Clad, which is used for floating point error analysis, is transformation based. And here I would like to call up on our virtual stage, Mrs. Garima Singh, to dive a little bit more into the details about the work she did as a Google Summer of Code student. Garima, take it away.
Okay, thanks, Vasil. Now I'm going to be talking about the tool the floating point error estimation framework is built on, and also be discussing a small case study, which will basically showcase the capabilities of such a floating point error estimation framework. Okay, so let's get started. So we all know that we need AD, and how we accomplish this is using Clad. So Clad is a source transformation AD tool. It is implemented as a plugin to the Clad compiler, which means that it inspects the internal compiler representation of the target function to generate its derivative. For example, giving the source code of a function, here it's sqr, that calculates the square of the given input, Clad can then generate a function that returns its derivative. So if you do this, you'll get something like this. Here the function would be sqrd arg0. And as you can tell, this function indeed calculates the derivative of sqr, which is 2x. Okay, so there are a lot of AD tools out there, but why do we want to use Clad? So there are a lot of advantages to Clad's approach. Firstly, Clad requires little to no code modification of computing derivatives of existing code bases. Secondly, it also supports a large subset of C++ constructs and ongoing development to support CUDA programs. This means that we can estimate error on most modern C++ constructs and soon even for CUDA programs. And as Vasil discussed earlier, it has some truly impactful uses. Clad is also scalable, thus allowing scalable error estimation for large and complex code bases. Lastly, it is well integrated into the compiler, allowing us to automatically generate FP error estimation code. Okay, so now we know about Clad. Let's take a look at the bigger picture of how Clad and the error estimation framework come together. Since Clad is a Clang plugin, Clad hooks onto the Clang compilation pipeline. So control flow from the Clang compilation pipeline passes on to Clad. Clad then identifies if a call to estimate error was made. If so, it transfers the control flow to the error estimation handler, which is responsible for initializations and other housekeeping tasks. The error estimation handler then dispatches a call to Clad's gradient generation module with the right settings to perform error estimation code generation. There is also a module here called the error model, which is the part of Clad that represents the error estimation formula and the part that is also fully customizable by the user. This is something that we're going to discuss in the later slides. These two modules, the error model and Clad's gradient generation module, then communicate and exchange the errors and derivatives with each other. Once the whole process is done, we get the generated error estimation and derivative code. And finally, the control flow passes back to the Clad to complete the compilation of our original program. Now, on the user side, the process looks much better. Firstly, we come up with a function to estimate the error of. In this case, it is func, a function that returns the sum of its inputs. Then we want to call estimate error on it from our main function. Once the estimate error call is processed, Clad returns the generated code wrapped up in a Clad object. We can access the underlying function that Clad generated using the Clad object using the function execute. Here you can see execute returns the total floating point error in the function as the last parameter that you can then print and utilize in your analysis. Okay, so that was about just estimating errors, but the floating point error estimation framework is capable of much more. While you can still just use it to satisfactorily estimate floating point errors in the input function, there's a lot more information we can extract from the intermediate floating point errors. One such piece of information is sensitivity. As the name suggests, the sensitivity of a variable gives an idea about how sensitive a particular variable is to FP errors. So the lower the sensitivity, the less likely is the variable to have a bigger impact on the total floating point error in the function. A general definition of it is as follows. Here, the del f by del xi is the derivative of this function with respect to the variable whose sensitivity we want to calculate, and xi is the value of the variable. If you recall the simple error formula we derived a few slides ago, you would see the sensitivity only differs from it by a constant factor of the machine epsilon. So only in this case, both the terms can be used interchangeably during comparison. A more complex error model may not have such a direct relationship with the sensitivity. As I already mentioned, the more sensitive, the more prone a variable is to floating point errors. This has very interesting implications for the numerical stability of algorithms and also builds the foundation for a set of type optimization techniques called mixed precision tuning. Mixed precision tuning involves demoting certain types to lower sensitivity and subsequently a lower error contribution to the function's final error. Okay, so let's talk about a simple case study that demonstrates the use of Clad to perform mixed precision tuning optimizations. Here, we introduce a simple program called Simpsons that calculates the integral of a function over the interval a to b for about 1,000,000 iterations. For this for the Simpsons for the function for Simpsons to integrate, we use the function f. Here is the function to define a math function y equals to pi into sine x pi, whose integral over the limits 0 to 1 is 2. As you can see, currently all the variables are in non-standard 10-byte extended precision, that is long double. However, as we will see later on, this might not really be necessary. Okay, let's look at some floating point configurations, their errors. So note, we run all of this analysis using the values of a and b in the Simpsons function to be 0 and 1. That means the Simpson function calculates the integral of the pi into sine x pi function over the limit 0 to 1. And the actual answer for that is 2. And then it compares them with the ground truth value of 2. Okay, here is the table. So having a closer look at the table, clearly we can tell the only two competing values here are the long double and the double precision. The single precision value provides very poor results. Here, when I say better precision or close or better accuracy, really is a problem dependent thing. Choosing the correct precision configuration is largely, as I said, a problem dependent thing. For some problems, even long double precision can fall short, but for some problems, the double precision accuracy is good enough. For the sake of this case study, we assume that we want all variables and subsequently the result to be under the strict threshold of 10 to the power minus 12. As you can see, Clad provides a fair estimate of the upper bound of the function error in the functions. So while it is not exactly the same as the absolute error, it does provide, and as we discussed before, it always provides the asymptotic error bonds at the end of FP error estimation. So the default model provided with Clad does something like this. But if you want to implement something that gets better estimates or more closer estimates, and you're okay with underestimating the error, you can use a custom model. And we will discuss how to create a custom model later in the slides. But currently we use the default model because it's general enough and it gives us good upper bound estimates. Okay, let's move on. So before we go on and discuss the results, let's take a look into what the generated code actually looks like. So let's look at the function f, for example, and then its generated code. So the function f is on the left hand of the screen and the generated code is on the right hand of the screen. And now it looks super complicated, and it is actually much longer in reality because it also has to calculate the derivative. But right now we can just look at the error estimation specific parts. So here are two important variables that we want to look at. First is the final error. Final error basically accumulates the error in the whole function, accumulates the floating point error in the whole function, and then returns it back to the user. And secondly, the delta prefix variables, which accumulate the total error contribution of each variable they are prefixed to. Here you can see the delta variables of TMP and TMP2, right? Coming to the formula on the right of these delta variables, we can see that the underscore d underscore prefixed variables basically are the derivatives of the function with respect to the variable they are prefixed to. The underscore EE REPL underscore prefixed variables refer to a copy of the variable at that instance in time because you can have reassignments for the same variable and you want to retain the copy at that specific time. And finally, the really long number at the end, you see, is the machine epsilon. In this case, it's for a long double because that's the type of the variable. And you can probably tell that this conforms to the error formula that we established previously in one of the definitions. Okay, we have all the info we need now. But how exactly do we figure out which variables to keep in high precision so that our error is lower than some threshold? So Clad can help in that. So Clad calculates the total error contribution of each variable in the target function. Then we can actually ask Clad to either print it to standard output or a file. Clad will then print the errors in this format. So we have a variable name and then the error value associated with it. It is also possible to customize what is printed. For example, you can also print derivative info or even sensitivity information this way. Finally, once we have all this information, we can just pick out the variables with a higher error than a set threshold and keep them in high precision. Okay, now let's look at the Simpson's function once again. With the Simpson's function, we identified two variables, s1 and x, that had the error values over our set threshold of 10 to the power minus 12. We also plotted how the sensitivity changes across the iterations in the Simpson's code, which is then highlighted by purple. So here you go. These are the sensitivity trends of both of the variables. This brings up an interesting point. The sensitivity of variable x increases over almost the first half of the run and then decreases later on. And to note here, this is the change in sensitivity. The total sensitivity would then be a sum of all of these values, all of the y values in this graph. Okay, coming back to it. So this trend actually tells us something very interesting about more aggressive optimizations that we can apply. And we'll look at them very briefly towards the end. Okay. Now, finally, we can apply the mixed precision configuration we got from Clad to the functions. So in the Simpson's function, you can see that we only kept x1, x and s1 in high precision, and we changed everything to lower precision. In the f, nothing really has changed. Now, the moment of truth. We see that Clad's mixed precision recommendation, which is on the second element here, gives almost the same accuracy as the pure 10-byte extended precision, while saving on 6 variables being in lower precision. And as for the implications on speed, the mixed precision configuration is up to 10% faster than the pure extended precision one over different values of n. We also see that Clad's estimated error on both configurations is also the same. So you can see that the 10-byte extended precision has a very, very similar estimated error upper bound as the Clad's mixed precision. This can be helpful to determine if the mixed precision version of a program is as accurate as the extended precision one when an accurate ground truth is not available. So even in the cases, even when you have a really different upper bounds and different absolute errors, it still might be beneficial to have such an estimate because then you can use it to compare your mixed precision results. Okay, so as I was mentioning before, we can do some aggressive optimization. So let's look at that. More aggressive optimizations can also be performed after having a close look at the sensitivity of the variables across iterations. Let's recall the variables x and s1. So we have s1 here, and then we have x here. Here we can see that the sensitivity of variable x peaks at about the 600th iteration. This may imply that if we keep x in high precision with the first half of the loop execution, because those turn out to be more crucial in determining the total error contribution by x. So you can see the first half, the change in sensitivity is growing as the iterations go on and it reaches a peak. However, it is important to note two things here. Splitting the loop for x may mean that x may be used in other high precision expressions, leading to implicit casting, which might affect the overall performance. And second, if there are closely related variables that show a difference in the sensitivity trends, like here how S1 is increasing across the iterations, achieving a maximum at the very end, it might not be very beneficial to spend time performing such complex optimizations. Lastly, it is also important to note that an effective mixed precision configuration has to be made while keeping in mind the overhead of implicit casts and the variety of input data sets to the problem. The good thing here is that such information will usually reflect in the sensitivity trends over different data sets and executions. So this concludes the case study. Now, with the little time we have remaining, we also demonstrate how to use a custom model. Okay, as I talked about before, Clad also supports the usage of custom-defined models. Firstly, all you have to do to define your own model is implement the FP error estimation class, which is a generic interface that provides the error expressions for Clad to generate. Then, in that class, you have to override the assign error function. This function is called for all LHS of every assignment expression in the target function. So what does the assign error function do? It essentially represents the mathematical formula of the error model that you're using in a form that Clang and Clad can understand. This form is usually used to generate the code. So in the assign error function, you actually get the reference to the variable of interest and the derivative. Then using those two pieces of information, you can do whatever you want. You can basically create any error model that you want. And then it can also be dynamic because it is generated for each and every assignment operation. So yeah, and in turn, what you have to return is the error estimation formula, which will then be used to accumulate the error. As of now, filling in these functions requires knowledge of the Clang APIs. We plan to provide higher-level APIs to make it simpler to use. But meanwhile, we're happy to provide assistance in writing custom models if necessary. For more information, how to build a custom model from scratch, you can check out a demo linked in this slides. And for more information on the FP error estimation, you can also check out the second link here. Finally, to conclude this presentation, I'm just going to give a summary of what we talked about today. So we present an AD-based FP error analysis framework that helps identify the largest contributors to FP error in a function and also enables further FP analysis such as mixed precision tuning. We also present Clad, a novel customizable AD-based error estimation framework that automates FP error analysis. Clad is also available to download with Conda. We present a case study on sensitivity analysis and mixed precision tuning of a Simpson's rule function. We also illustrate how to create a custom FP error analysis model capable of incorporating domain-specific knowledge. In the future, we plan to add functionality to use the mixed precision recommendations to automatically generate optimized code, which will allow further research in the area of lossy compression. Lastly, you can find Clad on GitHub or through the interactive Jupyter notebooks linked here. That's all. Thank you so much. And yeah, now we can open the floor for questions.